Salve ragazzi. Okay. I think that we can start. Can you hear me? I attached the earphone. Okay, perfect. Okay. I want to. Hello, Anil.
Hello, Professor.
Hello. I want to start the lesson with an exercise with an application by using deeds. And I want to ask you to implement a an 8-bit adder, an 8-bit ripple carry adder, RCA. In particular, I want that you firstly implement the full adder, and then you use the full adder in order to implement in a hierarchical way, in order to implement the 8-bit adder. To do so, I want to show you a feature of deeds that I think that I did not show before. I'm sharing the screen. Okay. Now, could you see the simulator?
Yes. Yes.
Yes.
Yeah. Okay. Perfect. Now, I want to show you the possibility to define a new component. A new component in a similar way that the other components that are present on this row of the menus. This new component must be defined by using file, new block here. Now, this is quite similar to the previous version. If you see here, for example, the input and output options have changed. These new options allows to introduce pins that are the symbols to indicate that these points can be used as input-output of the new component that we are defining. Then, here in this area, we have to build the circuit, and then we can use this sub-window here to describe the symbol. The symbol is automatically updated with the input and output that we define and with the name of the component. Okay, for example, if I want to realize a buffer composed by two inverters, I have to place a NOT here and then not here. I have to connect them with a wire. Now, to define the input and output, I have to put this block input pin here. Input pin, it is a 1-bit pin. I can give it a name, for example, A. Okay. As you can see here in the sub windows, the component, the square is updated with now the input A. At this point, I have to connect this one. Okay, perfect. And the same happens for the output. I have to click here, this option, block output pins. And for this application, it is enough output pin here. I, for example, wires to connect the outputs. And then that's all. You can see here, for example, now that I have A and Y, and just to give a better order, I could move this pin Y, for example, on the right side here, move A one position below. Okay. The name of the component, for example, buffer. Okay. And then I can save this, save as, and I can use, for example, the same name of the component, so buffer. The extension of the file is different from the DIDS project. It is a circuit block file, CBE, save. Okay, that's all. At this point, we can, for example, now define a new circuit. Okay, now in this circuit, we can use the new component, the buffer, by clicking here, custom components, circuit block elements, buffer, open. Okay, you can say label buffer 1, for example. That's all. And this block is fully functional. Unfortunately, DIDS doesn't allow to build more hierarchical levels. For example, I could expect to build a second level by using this buffer, and then namely to define another component by using this component, and then use the second component in a project. It is not possible. I can define just one hierarchical level, so just one component. For example, in the case of an adder, more hierarchical levels are useful, for example, to build in a first level an half adder, in a second level a full adder, in the last level the 8-bit adder, ripple carry adder. That's not possible, so we have to define one only block that is the only CBE that is a full adder. If you want, obviously, you could create two different CBEs, one for the half adder and one other for the full adder, but the full adder cannot be derived from the half adder. It must be built as a standalone project. Okay? Is it clear? So you could use, I was asking to you to use a CBE to build a full adder operating with just 1 bit, and then use this CBE to build an 8-bit adder, a ripple carry adder. Okay?
Okay.
Please. You have 2 minutes and enough. I hope that you already tried to implement or to simulate an half adder or a full adder. Am I right? No. Please don't forget to use these. Don't forget to implement circuits that we are seeing during lessons. Not all, of course, but some important circuits like half adder, full adder. It is a very important exercise. Obviously, you could implement also a multiplier if you want. Not today, not at this lesson, but also in that case, you could use a hierarchical project by defining a custom component. Obviously, in that case, the custom component could be the basic block of the multiplier composed by a full adder and an AND gate. Okay. If in the case that this circuit block symbol editor, this sub windows here, doesn't open, you can recall it by using tools, not tools, but view. Okay, view. Show symbol editor here.
Prof, I have a problem. I can see this in view. I see just show bird's eye view. Okay. I don't know what is this.
Where here show
Yes.
bird's eye view. Yes, but you have to start the component editor. You have to start not a new circuit but a new block.
Sure. Okay, thank you.
New circuit is the normal simulator. A new block is the one that allows to create this block.
Okay, thank you.
No, the bird's eye view is a view of all the schematic. A bird's eye is a top view. And if you are creating a complex schematic, the view allows to have a full view of the world that you are working on.
Okay.
Obviously, this application is useful just to fix your memory on the structure of the full adder, on the operation of the full adder, and the way it is used to build adders. Okay. One suggestion is to simulate, firstly to simulate the full adder. You can do that by first creating the component and then start a new circuit to instantiate this new component and then simulate it as a standalone block. I always suggest to proceed in this way. You have first to simulate the subparts of your project, because in this way it is much more easy to identify errors, problems in general. It is a very good practice. It is a mandatory practice. Just an information, but this sub window, this circuit block symbol editor here that I'm moving in this moment, could you see it? Ah, okay. So it is considered a part of this window, okay, of the main window. Perfect. Have you finished the full adder?
Almost.
Only Verdiana, Francesco, Andrea, Alba. Yes, but have you simulated it? That's a problem, you have to simulate it.
But in order to simulate the circuit, we have to exit from the circuit block to use input switch and output switch.
Yes.
Ah, okay.
Okay, I have the same problem.
Okay, you have to finish this block, this component, and to start the new circuit here. So this simulator starts, and you can recall this block into the scheme, into the circuital scheme. It will appear as one block, the block in this editor. Okay.
Okay.
Okay, once saved, you can use File, New Circuit. I don't know if the Windows is shared. I share another one. the circuit CBA PBS. Okay, this one. Now from this Windows, that is the simulator, you can use this button here, custom components. From custom component, you have to click here, circuit block element. And then, for example, in my case, I named it full adder. Okay, click here, full adder, open here. A label is asked, but it is a label just to differentiate this instance from another one of the same type. For example, if I will instance 3 or more full adders, the way to separate the first one from the second one, from the third one, and so on, is to use different labels. For example, in this case, I can use FA1, but it's just a name. You can use the name that you want. Okay, at this point, if you want to simulate it, yes, you use right. You have to use, for example, input switches here. One switch, for example, A, another one, for example, B. The third one, input C in, okay, and 2 outputs, and for example, S and C out to finish. Interconnects here, wires, no. Okay, this is the setup for simulation. Here you obviously have to save it. FA. And now you can simulate, and I suggest to use the transient simulators. Hereby click this timing diagram simulator. Okay. At this point, you can set A, B, and C in order to make all the combinations. No, for example, here I can give A start from 0, then 1, another one time 0, 1, 0, and once again 1. B, for example, B starts here, goes down here, goes up, and then down here, up, and down here. The last one, C, for example, could start here. Here I have a B, A and B 0, 1, so C high. C continues to be high with A high. Okay. Then B goes down. Okay. It's a good solution. Here. Here and here. And here. At this point, I have all the combinations. I have to put the final instant for the simulation with this cursor here. And then see the simulations by click this button. Okay. If you want, you can enlarge the outputs, S for example, or C out for example, to gain more space from the input. If you want, you can use this cursor to see the values of the waveform where you are. You can follow the timing propagation of the input. However, the important thing that you can compare what happens here in correspondence of the different combination of the inputs. So, for example, in at this instance, we have A, B, and C that are high, and indeed we have S that is I and C out that is I. Okay, so it is correct. Here we have A and B and C that are 0, and we have the output that are both zeros. When instead only two inputs are high, for example, in this case B and C in, and A remains low, here we have a C out that is high and S that is low. And another combination here, for example, we have that A and C in are high, but B is low, and also in this case we have that S is low and C out is high. Okay, it seems working right. Okay, at this point you can stop the simulations. Then you can start a new circuit. Okay, and at this point you can simulate the 8-bit full adder ripple carrier. I want just to show you. Oh, just a moment. Add 8-bit add. For example, you can make in this way. 8-bit adder. Are you seeing my screen?
Yeah.
Okay. And for example, in this case, I instantiated 8 full adders here. Okay. Obviously, the only one connection between the full adder concerns CO and CE, obviously that are carry out and carry in. That obviously, since it is a ripple carry adder, clearly they are connected in series in this way. Then for the input, obviously, in this case, I connected only one of the input A. If you want, you can use an input switch, a single input switch for each of the inputs. So for example, for B here, we could use, for example, B0, okay? And then we connect this switch, this input switch here in this way, and then, for example, use another input switch for B1, and so use the label B1 and connect this one to this one, and so on. It is always possible, or eventually you could use these in the submenu input deep switches. Here we have, for example, 8-bit switch here. We can use, for example, B in the same way that I used for the input A, and we can use the only switch here for these inputs. Okay, so we have to connect then these outputs to this one. This one, the second to this one, the third to this other one. Oops, there is a bad connection here. Okay. Then, of course, we have to select also the input switch for the first one, C0. We named it C0. It is just one bit, C0, for example. Another Y here. And that's all for the inputs. The outputs, we have to proceed in a similar way. We here have 8 outputs that must be connected to the output of the single full adders. And in this case, oops, okay, this one, we have S0. In this case, the label should be selected carefully, because in this case, during simulations, now this bit these bits have an order. So the S0 is the least significant one. So it is important to understand if the result is correct. So it is important for the coding of the result. So in this case, it is important numbering correctly the inputs. Here we have that the full adder plays the first full adder here is the full adder related to the least significant bit, and obviously the full adder at the rightmost side of the picture here is the most significant one. So I could use S0 for this one, I could use S1 for this second, and so on. S2, S3, 4, 5, 7, and obviously the carry out. Here. And so the connections. Okay, you could say, you could also check about the correctness by clicking this button. As we have no messages, so the circuit, or at least the scheme, from a formal point of view, should be correct. Okay, we just need to make some simulations. Okay, now the simulation window is very populated now, and we have here, for example, A and B. Oops, they appear as a single switch, but if you want, you can enlarge them. Sorry, enlarge this one. Oops. A. Okay, I can enlarge them. For example, A, and in this case I can set the single bits. So the bit 0, for example, the bit 2, bit 3, and so on. Or eventually I could set directly here all the bus A with the same cursor. For example, here, if I click at this point at this instant on time here, these windows, small windows, opens, and here I can set the values here in hexadecimal. They are, I want to remember that they are 8 bits. In hexadecimal, we need over 2 numbers. Each number corresponds to 4 bits. So in this case, obviously here you can see also the conversion in binary. So for example, if you want all the bits equal to 1, F, okay, and as you can see here, we have all the bits equal to 1. Then here we can see the same thing for B. And for B, for example, we could set B equal to 1. Okay? Then at this point, we have to set this one and make simulations. Oh, sorry, the same thing for scene. Scene in this case, obviously, must be 0. Oops. Is a problem. Okay. It must be always 0. Okay. Perfect. Okay, I want just to that you note that since we are working with a ripple carry adder, which means that the carry is propagating from the least significant bit here up to the least to the most significant bit. It is important to observe that the maximum delay is observable only if the signal goes through all the full adders, so propagate from the beginning to the end. Not all the combination of the inputs allow this behavior. For example, if I just had all zeros with all 1, I have that the outputs are all equal to 1, but no carry is propagating. If I want the maximum delay, I need to observe the condition, the configuration of the inputs that cause the propagation between all the carries. And for example, a particular configuration could be A equal to 1, all bits of A set to 1, and just one bit of B, the least significant bit of B, equal to 1. Okay, in that case, if you look at the addition, you can see that starting from the least significant bits, I make the summation 1 plus 1. This addition gives rise to a carry equal to 1, that go to add to the second sum. The second one generate a third carry that sum to the third sum, and so on. So all the full adders generate a carry bit that propagates, that add to the subsequent full adders and generate the maximum delay from the beginning to the end. Is it clear to you? To all of you?
Yes.
Yes.
Yes. Yes.
Okay. Okay. That's the reason why I selected here for A here FF and for B 01. Okay. Perfect. Now, at this point, I suggest to save this input waveform. I want to remember to you that you can save by clicking here, test sequence unnamed. You can click and store as. You can give a name to this test sequence. Test sequence 1 is okay for me. Okay. Perfect. Okay. You can close this window. You can save the project to save the waveform. Okay. At this point, I propose to you to modify this ripple carry adder in order to implement also the subtractions. Okay. Okay. Just a couple of minutes of rest, and then we can start to modify this circuit to consider also the subtractions. The exercise will end approximately at 4, and then we can use the last hour to introduce the registers. We have to start the sequential part. To start the sequential part, we have to learn how register work. Okay, a couple of minutes of rest, and then we can restart.
Okay.
Okay. Okay. Have you finished? No. You were in rest. Okay. Not yet. You were in rest, sorry. Okay, now. Do you remember the modification? For the modifications, you have to use multiplexers here. Inverters here. Not here. Here, sorry.
Lei mi deve dare un numero.
Now we have to. I want to underline that multiplexers can be found here. You can need this component, multiplexers, and in particular you need of one multiplexer, 2 inputs and 1 outputs. These are the 2 inputs, and this is the selecting input. Okay? Yes? Yes, you have to use the bus, and you have to use a bus splitter. Here, this component. However, it is not so convenient. It is much more easy to use separate wires. However, clearly you have to modify this one. You have to delete these lines. You have to add for each full adder a multiplexer to1. You have to add an inverter. Okay, and these must be used for each one of the B inputs. In particular, you have that B you could, for example, make this change. And you could use this one here. Okay, at this point you just to make the project custom here. Perhaps we could move this one all this one on the right here. Okay. Perfect. Probably here and probably here. Okay. Perfect. It has more sense. Okay. Oh, this one. This one. This one. This one. And this one. Then, at this point, the first bit here, B here, and B is here. And then B is here. And here, okay. No, sorry. There was an error here. Okay. Now it's correct. Here. Here. So far. And here. This way. And in this way. Okay. And so on. So we have okay. So 2, 3, 4, 5, 6, 7, 8. Okay. And the last one. Okay. And now at this point, you have to select another input, to add another input, add and sub. Obviously here we have to set another multiplexer. Here we have to use an highly logic level. And this other input is for a logic low level. Okay. The last input okay, that is the add and sub. And for example, we can put this here. But it's not so good here. From here, and then no. Here, okay. 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 Verdiana, you can see the usefulness now of this bird's eye view.
Yes, now it's clear.
Because if you are working with a very zoom in, you have to move. You can move in the project without losing the position into the project where you are. Okay, at this point, we're going to start the simulation. And for the simulation, I don't know, but we changed this one. Okay. Okay, with the load test sequence, we already set the old signals. Obviously, we have to set the new one. Okay, so we have here the add and sub. Here it is 0. But for example, we can try to make the difference from here. Once again from here, and nothing. We have to this one, and then start the simulation. And for example, here we can see that we are making here in this point, here, we are making 2 minus 1. Here I presume. Okay, 2 minus 1. Here, sorry, here 2 minus 1, okay. Because add and sub is equal to 1, we are making the summation, the differences, and then the output is all bits are 0 and the 1 is 1. Okay, I placed the input A and B in casual order. In this case, the only one value that I placed in some kind of attention was for this one, FF for A, and FF for A and 1 for B. Here we can see the addition and here the subtraction. And you have to see if all the results are correct, essentially. So I don't know. Yes, I can leave you the work to verify if the circuit operates correctly. Obviously, you can change the input as you want, just to try several configurations. And I want to remember that the outputs, when you make differences, the output is coded as a choose complement. So if you find that the most significant bit is equal to 1, you have to consider the number as a negative number. And so in order to identify what is the decimal value, you have to complement each bit and then add 1 bit in the least significant position. In any case, I suggest you to save this circuit and to use it, for example, for subsequent exercises. We will use, for example, this kind of circuits for to implement, for example, timers, counters in the next lessons. Eventually, you also could to modify this scheme in order to substitute to this block here, full adder, this CBE, to substitute them with the implementation. It could be useful, for example, if you want to use this ripple carryout as in turn as a CBE, as a block element that you have to use in another circuit. It is not mandatory. Only if you want. It is you can use this circuit as is without modifications. Okay. I don't know if you have any questions. Obviously, you can also observe here, for example, here we introduced this input add and sub to select these multiplexers, okay, but I didn't pay attention to the position of this add and sub. For example, here, if add and sub is equal to 1, what is the version of B that is passed to the full adders? Is the negative function? Is the negative version? I don't know. So you could also check this step and to verify the correctness. Obviously, if you could also to use this add and sub as a active low signal, namely it makes the subtraction if it is low and makes the addition if it is 1, or an active high where it makes addition if it is 0 and subtractions if it is 1. These are several configurations, but these configurations are essentially degree of freedoms of the designers. So you can change as you want. Okay, are there any questions? Sí, yeah. Yes, that's I said. That's I said. Exactly what I said. If you change that block, if you make explicit that block, you can use this. Okay. Yes. Of course, if you want, you can use that block. Obviously, yes. Yeah, but this clearly this exercise is to make you practice with the implementation of the ripple carry adder. So it was important for me that you use the single full adders in order to recap as a full adder is made, how it works, how it can be combined to make a full adder, then a ripple carry adder. Obviously, if you don't need to make this kind of exercise or to in some way explicitate how another is done, you can use the component, the predefined component that is part of DIDS. It's clear. Okay. Now, if there are no other questions, I can switch to another topic. It is a very important topic, so I want to start gradually. And I think that we will finish this topic. I don't know for tomorrow. Most probably for the next Monday. Then we will use this topic, these registers, to implement sequential circuits and also finished machines and circuit for the control of elements. We have to put together these registers with the combinatorial part that we have learned during these lessons up to now. Now, let me to switch. Okay. Okay, can you see the sheet of the iPad?
Yes.
Okay. Now, up to now, we have learned how combinatorial circuit operates. Combinatorial circuits, how the name says combinatorial, simply make a combination, calculate a function that is a mere combination of the input signals. So a circuit that simply, for example, make a two-level function, an AND or invert, A, B, or C, for example. Okay, that's a combination of the input means that this y depends only on the value that A, B, and C take in that moment. If we change the value at A or at B or at C, immediately the value of y change regardless of the story of the input. Namely, if we want to say this concept in other words, we can say that in this expression there is no the time variable. Okay, all this calculation do not depend, this calculation, but all similar or combinatorial calculation do not depend by time. Okay, so it means that, for example, imagine that you want to make a circuit that identify particular sequences. Imagine, for example, that you have a machine. That machine operates in a way if receives the sequence 1, 1, 0. Operates in a different way if receive the sequence 0, 1, 0. And imagine that this machine works with one input bit. Okay, so it receives first 0, then 1, and then 1. In the first case, in the second case, it receives 0, then 1, and then once again 0. Now, if this machine was implemented by a combinatorial or was controlled by a combinatorial circuit, it was not possible to distinguish these two operating conditions. Indeed, if this the circuit that control, if you imagine that you have here the machine, then a control, and this control is implemented with a circuit that is a circuit, a combinatorial circuit. Imagine that it has one bit input in, and its input could be these sequences. Okay, now at a certain instant of time it arrives at 0, 0. Okay, at a second instant of time it arrives at 1. Okay, and then sorry, for example, in this case, suppose that the second sequence is composed by all 1, 1, 1, 1. Okay, so it arrives at 0, arrives at 1, then arrives at 1, then arrives the last one. Now, the two sequences are different, and the two sequences means that the circuit, the control circuit, must configure the machines to work in two different ways. But if we are using a control circuit that is composed by a combinatorial circuit, we have just to consider this, the output of these control machines depends only on the last bit that is arrived. Since in this case the last bit is for both configuration equal to 1, the output of the control logic will be 1. Okay? This is why this control logic is not capable to work by considering the story of the input, the past inputs. If we could introduce this capability, then in this case things are very different, because in this case, when we are arrived at the last one of the configuration, then the last one is a part of all the sequence. Then the machine remember that the previous two inputs will be 1, 1 in the second case and 0, 1 in the first case. And so it makes the difference between the two situations. This is not the only case. There are a very large number of cases where we could make an example of this kind. Namely, it is very important to introduce for these circuits the capability to remember the past inputs. Now, machines of circuits of these kinds are called sequential machines, or sequential circuits, if you want. Machines as a synonym of circuit. However, sequential because it is capable to identify sequences. However, one of the most important components of these sequential circuits is a component that is capable to introduce the time variable. Namely, it is capable to make that the circuit could remember something. Okay, that means that if the input at a certain time change, then the output, for example, could remain constant, because its value could depend on the combination of this input and in particular the story of these inputs. Now, in order to understand how this particular component, that remember is done, we have to understand that this circuit, that we are working with the binary circuit. This is a very important advantage in this case, since this help to implement this kind of circuit, this kind of remembering circuit, so circuit that make possible to store, to register the past inputs. As I said, to implement this kind of circuit in a much more easy way that if we should use in the case of a different coding or a different algebra, for example, for an hexadecimal or a decimal algebra. For example, consider that you have a schema like this one. Consider that we have two NOT, imagine NOT 1 and NOT 2, and imagine that these NOTs are connected so that the output of the first one is the input of the second one, and in turn the output of the second one is the input of the first one, in this way. Now, imagine that this input here we use in 1 that is equal to out 2, and out 1 that is equal to in 2. Okay, now imagine that you want report on a graph the curve that the characteristic of the knot, the curve that describes the behavior of the knot. So imagine, for example, to use a graph here that is reporting with reference, for example, to the knot 1. We report out, in 1 and out 1. Okay. If the knot is an ideal gate, namely if we don't consider the eventual parasitic element that come out from the physical implementation of this gate, but we only refer to its logical behavior, we can describe this characteristic in such a way. Here we have 0, here we have 1, and here we have 1. Is it clear to you? This curve, what is saying? This curve is saying that if the input here, but with reference to a generic inverter, imagine that we here have in 1 and out 1, okay? With reference to this generic inverter, we have that if in starts from 0, if in is 0, the output is 1, okay? And so is the curve. If the input is 0, the output is 1. Then, if the input varies, moves along this semi-interval of possible values from 0 to 1, all these values of the input are interpreted like a 0, okay? And so that means that the inverter, the NOT gate, gives at the output an I value 1. Then, if the input assumes value near to 1, then the output of this NOT goes to 0. Okay, is it clear to you? Just to understand to this part, you have to remember what we said about this the noise margin. Do you remember?
Yes.
In an ideal case, we have 0 or 1. Then, if we have 0, the output will be 1. If the input is 1, the output will be 0. Okay, and that's correct. However, we could have some noise, some disturbances on the 0, for example. Okay, but these logic gate are designed in order that if the input is not exactly 0, but is it is 0 plus a noise, for example, then we, for example, we don't have exactly 0, but we have a value that is slightly higher than 0. For example, we have a value that is placed here. Then, in that case, the output of the gate continues to be equal to 1, continues to be high. Namely, this logic gate is robust to noise and is tolerant to noise, and in particular it filters the output from the noise, no? Because at the output we don't see the effect of this variation due to noises. The same thing happens if we have an high input. Here, for example, if we, instead of having 1, we could have, for example, a slight lower value, for example, placed here, okay? But once again, we have a noise margin. The gate is tolerant to noise, so it eliminates these contributions and returns an output that is always 0. Okay, so the note continues to be a note even if the inputs are not exactly 0 or 1, but they are 0 and 1, but they could affect from noise, by noise. Okay, so this is the curve that describes this behavior. Just to be, oh sorry, okay, I pushed the wrong button, sorry. Now, just to be more precise, this curve is an ideal curve because the real operation of a note does not follow exactly this curve, but it is an approximation of this one. Just to give you an idea, the real curve is something like this. Okay, there is a transition region from here to here that could is composed of values that are not exactly 0 or 1. They are not well defined. And here there are a lot of techniques to improve this curve in order to make this region very narrow. This region should be ideally a delta, an impulse here. It is not possible, and it has a finite extension. We electronics engineers in general works. The electronic engineers that works on this topic in particular works to make these regions quite smaller, so very narrow. In any case, for our cars, it is more than enough that if we consider this ideal curve. Is it clear to you? Are you following me?
Yes.
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 At this point, we have this characteristic. I said in 1, out 1. And we have this characteristic. Okay, now then come back to this configuration now. In this configuration, we have a second inverter. This inverter works with inverted signals with respect to the first inverter. So for the second inverter, we have that this abscissa that really coincide with this other axis. We have here this coincide with out 2, and this one correspond to in 2. Okay, so at this point you can put only in this on this plane, you can put also the characteristics of the inverter 2. However, in order to make so, you have to consider that this diagram must be rotated and flipped. So you have to imagine that this is rotated in this way, and then flipped. Rotation give rise to this diagram. And the horizontal flip give rise to this other one. Now the axes are in 1 and out 1, and once again they coincide with in 2 and out 2. Okay, now on this axis we can plot the same curve that we used for the first inverter, this time for the second one. So this is for the first inverter, inverter 1, and then we can plot one other for the second one. This is for the 2. Do you agree? Is it clear to you? Okay. Now, from these two curves, the intersection of these two curves, we can observe 3 points. These points are this one, and this other one. They are important because they represent the 3 points where the two characteristics intersect. Namely, they represent the points where this configuration, this circuit, can operate in equilibrium conditions. Okay, what it means? If you assume that, for example, you change the input, you change in 1, apply an impulse to in 1, you are applying a perturbation to the state of the circuit. So the circuit begins a transient behavior. The transient behavior implies that, for example, the output of the first inverter change, so the input of the second inverter, and then the output of the second inverter. But after a transient, after an interval of time, this transient finishes. When this transient finishes, the circuit reaches a new equilibrium condition. Now, the new equilibrium condition will see the circuit operating in this point, or in this point, or in this point. It is not possible that in equilibrium the circuit operate here, for example, because at this here we have two different points. These two different points could be eventually possible only if the system is in a transient condition. Okay, but if it is in an equilibrium condition, the only three possible positions are this one, and this one. Now, for a number of reasons that you very probably don't know, because you should need of other information about the stability of circuits, stability of amplifiers in particular. For a number of reasons, two of these points are asymptotic stable points. One of these is is not asymptotic stable. In particular, this is an unstable point. This one. This point is unstable. By looking at the curve, you could justify this fact that by looking at the slope of these two characteristics. This point here is the intersection between the two characteristics where the slope is infinite. Here we have a slope that is infinite. In a real behavior, we have a slope that is very, very high here. It is not infinite, but it is, however, very high. Here we have a slope that is infinite, and the fact that this point, this equilibrium point, could be unstable derives from the product of the two slope of the two curves. Okay, so if this product is high, the point is unstable, is greater than 1. Okay, if this product, the slope is greater than 1, the point is unstable. If it is lower than 1, if it is stable. In particular, in this case, in the case of ideal curves, the product is infinity. So in particular, this point is very, very, very unstable. I repeat, in a real condition, here the slope of the curve is not infinite, it is very high, so the product is very high. But the consequences are very similar. Consequences are that you eventually could have the system that is positioned in this at this central point here, but it is unstable, so it is enough, for example, the variation of the temperature. Imagine that the circuit begins to changes its temperature with the operation. At the beginning it is cold, after some second it becomes very hot. Or for example, a little change in the supply voltage, for example. Okay, all these small variations makes that the circuit operation moves out from this central equilibrium point. Things are very different in these other 2 points, because in these other 2 points we can see that yes, we have here a slope that is very high, but the other slope is zero, essentially zero. Now the product of these 2 slopes should be, from a mathematical point of view, should be an infinity multiplied for a zero, so it is an indeterminate condition. However, in real cases we have that here we have a slope that is very close to zero. Here in the lower part have a slope that is very high, but it is not infinitive. The product between these 2 slopes gives a value that is is very small. It is certainly lower than than 1, sorry. This happens here for this point, but this happens also for this other point. This means that these 2 points are 2 stable, the point 1 and the point 2 are 2 equilibrium points that are very stable. That means that yes,
I couldn't understand that if the slope is very high, why it's not, why it is stable.
It is a problem to understand if you have no basic knowledge of analog electronics, of the basic of electronics. At this point, we have to believe me. Okay. The problem is that if you consider one of these points of this characteristic, you have to consider that the circuit is operating as is not operating in binary mode. It is operating as an analog circuit. That means that all the input values must be are processed by the circuit. Now, in particular, if we consider the slope of the curve in this point, the slope of the curve is, from a technical point of view, it represents the gain of the circuit. What means the gain of the circuit? The gain of the circuit means that if we, for example, we are considering this one, if we are working in this point, if we apply a very small variation to the input, we have a very high variation of the output. For example, you can see this by looking at this curve. This is an ideal characteristic, no? So imagine that you are here, are in this point. Now, imagine, so it means that the input is this one. Let me to use the green color. Okay, it means the input is this one. Now, imagine that you apply a very small variation to the input around this point. For example, imagine that you move here, or imagine that you move here. What happens is that the output suddenly switch to 1 in this case and to 0 in this other case, immediately. This means that the gain of the circuit is very high. In a real case, imagine that you are working on a real curve, this one on the right. What I was saying is that imagine that you are working in this point here. So you have this input and this output. Imagine now that you apply small variation to the input. Here you have that a small variation means that you are moving here, here, and then here. A small variation on the right side means that you are moving here. So, if you look at this curve, you see that at a small variation of the input correspond an high variation of the output. This means that you have an amplification. Namely, you have a gain that is greater than 1. On the contrary, if you are here, I'm trying to give you a graphical interpretation of what must be, should be demonstrated by using some equations. However, imagine that you are here, that you are working here, okay, with this input and this output, okay. Now, imagine that you move around this input. Your input slightly change. For example, we move on the right side here. If you move here on the right side, you have that the output, the new output is this one. Essentially, you have moved of a negligible quantity with respect to the previous output. The same thing happens if we move on the left side here. You essentially are around this point. The graphic is has no a resolution, so high resolution to show correctly the variations, but this means that variations are very negligible. The same things happens if we move here in the lower part of the curve. If we are working here, the output is this one. Then if we move around this point, we see that the output variations are very, very, very small. So this means that with at a variation of the input correspond a very, very small variation of the output. This means that the circuit is not amplifying, it is attenuating. This means that the gain is lower than 1. Okay, now, this is true for one inverter. Now, if we consider 2 inverters connected in this way, we have to consider that the resulting curve is, the real resulting curve is something like this, but it is quite different. This is quite this one, or like this one, or like this other one. Okay, now in this point, the gain of this circuit is given by the product between the gain of this one, of this inverter in this point, and of this other inverter in this other point. Okay, so since the gains of the two inverters are greater than 1, their product is obviously greater than 1. And this high value of the gain is responsible for the instability of the feedback of the circuit of the two inverters together, because it is enough that a small variation occurs at the input of one of the inverter, that immediately, because of the large gains, all the output begins to vary, to move very fast and very far from the equilibrium position. And so the circuits comes out from the equilibrium. On the contrary, if you are here, if you are in this point here or in this other point here, you have that the product of the gains is certainly lower than 1. That means if I try, if noise or a sort of disturbance occurs to change the input of one of the inverter, this variation is attenuated by gains that are significantly lower than 1. That means that the circuit altogether, it is very hard to move from this point or from this point. And that means that these 2 points are very stable equilibrium points. It is quite difficult to understand without a demonstration, but I hope that my graphic explanation has been useful for a little bit clarification with respect to your question. I don't know if it's true.
Yes, I understand, Professor. Thank you.
Now, in any case, this means that the circuit that we have designed, which is simply composed by 2 inverters connected in feedback. This kind of connection is also called feedback. The fact that the output of one circuit is connected to the input of the same circuit is called feedback. Gives rise to what we call a bistable circuit. Okay, so if we neglect this point, because I think that you understand that this point must not be considered as an equilibrium point. We have that the system can operate only in this point or in this point. Since there are 2 stable points, the system is called bistable circuit. A bistable circuit. But that's exactly what we need, because we are working with a binary algebra. A binary algebra needs of only 2 possible values. Now, if I have the circuit that can exist in 2 different stable points, we can use these 2 points to represent 1 and to represent 0. So 2 stable points associated with the 2 bits, not with the 2 values that a bit can assume. That means that this kind of circuit, since it is stable, can be used to store the value of a bit. This is only an operation principle because this circuit cannot be used as is, cannot be used because we don't know how to change the values stored in this circuit. If it's true that this circuit is stable, it means that at this point, if I have to change the value, I have to write a new bit in this bistable circuit, it is a very great problem because I cannot move it from a stable point. So I have to study some solutions, circuital solution. I have to apply some modification to this scheme in order to make the to add the possibility, the capability to change the value, so to write a value and obviously to read a value. But at this point the lesson is ended, so we need to continue tomorrow. Tomorrow we will start from this point and we will start to begin how bistable works. We will call this a latch, but we will see a number of variations, a significant number of variations that are able to add several features and to solve several problems of this kind of circuit. Okay, that's enough. If there are no questions, I think that they are 9 to 5, so the lesson is ended. You have to go to the lesson of Professor Pappalardo. If you have some question, I'm here. I don't know. No more questions? Okay. So we will see tomorrow, and so goodbye.
Bye.
Goodbye.
Bye.
Goodbye.